Okay, good afternoon. Sorry I sort of had that first bit of video interrupted, and I'm back to it. It's a few hours later because I had a couple of things I needed to attend to. So what we'll do is we'll go back to the PowerPoint. Hopefully this should seem relatively seamless to you, but I am splitting it into two videos. So we left off with our electrochemical cell, and it was a zinc cell with a standard hydrogen electrode. And we could see the zinc is being oxidized to zinc 2 plus, and the hydrogen is being reduced from H plus to H2, or vice versa. It goes in both directions. Give me a moment, I'll just make it so I can actually control the screen. So, where we left off was talking about how to draw a diagram to measure the electrode potentials of Fe3 plus and Fe2 plus. And in fact, I did actually put the answer up on there in the last one. So this is a good time for you to see if you can remember how to draw a cell diagram for an Fe3 plus, Fe2 plus in a half cell, maybe using something to work against to make sure we can definitely measure it. So I'll let you do that now. Pause the video whilst you do that. So I'm just going to reveal the answer to that one. We have a platinum electrode here. This is our inert electrode. We have our solution of Fe3 plus and Fe2 plus, both at 1 moles per decimeter cubed. So we don't just put in a solution of Fe3 plus at 1 mole per decimeter cubed. It's more like we put in 50% of Fe3 plus solution at 2 moles per decimeter cubed and 50% of Fe2 plus at 2 moles per decimeter cubed, because then when you add them together, they should then be 1 mole per decimeter cubed if we use equal volumes. We have our standard hydrogen electrode here, which is our standard and gives us a cell potential of 0 volts. And we have the Fe2 plus, Fe3 plus couple, which gives us a non-zero potential. So have you made sure you put everything in there? Have you drawn all of the reagents? Which one is the anode and which one's the cathode? Well, the answer is the anode is negative. Remember, we do not panic. And the cathode is positive. I don't know whether I said about it in the last video. I don't believe I did. But I used to teach when I was doing electrolysis. Panic, which is positive, is anode, negative is cathode. That is no longer the case. Panic is okay for electrolysis, but for electrode or electrochemistry, we do the opposite. So actually, positive is not the anode, negative is not the cathode. So for electrolysis, I go for panic. For electrochemistry, I always say don't panic. So we can see that this is the cell that we've made. We have hydrogen bubbling in. That is reducing Fe3 plus to Fe2 plus, and it is it's oxidizing itself to H plus ions. So what is the point of all this? Well, we are making a device that makes electronic or electric current from chemical energy, and of course that is the point of a battery. That's what batteries do. But there are more applications than that. So if any of you know about ships and things, sometimes you'll find big lumps of metal attached to ships, and what they're for is so that they corrode before the hull of the ship does. So they're called sacrificial blocks. Usually we use something like zinc because zinc has a high electrode potential, so it means that it will be corroded in preference to the hull. If we look here, we have a hydrogen and oxygen generator. This has lots and lots of ideas at the moment as to how to generate hydrogen as an alternative fuel. If we use some form of maybe solar energy or something to generate the electricity which powers this, we have a way of storing fuel. It's not as efficient as it could be, but actually we can store the chemical energy as hydrogen gas. Of course, we have our standard batteries, which we're used to using. This, in fact, is the diagram of a lead acid battery, much that's used in a car, and we can see that we have these electrochemical cells, sort of little mini ones in here, and we have a cell here, and then we have a battery of cells, which means that we have a number of cells joined together in series, which increases the voltage. We have hydrogen fuel cells, and this is a way that we can actually get electricity back from if we do this reaction. So we then put the hydrogen into the hydrogen fuel cell, and out comes electricity. Really, really important. The space shuttle, no, that's an old thing. The International Space Station actually uses hydrogen fuel cells, I've been told, to produce quite a lot of its electricity. And quite a lot of big ships and big industry use hydrogen fuel cells to generate electricity because it's quite an efficient way of generating electricity. They're thinking about changing electric cars rather than running on batteries to running on hydrogen fuel cells. The advantage being you no longer have to charge them. All you do is replace the hydrogen. The hydrogen then generates more electricity as you go. For those of you who are more biological, and you know I'm a little bit scared of biology, the photosynthesis, I can't even say photosynthesis, that's how much I love biology. Photosynthesis itself is an electrochemical process. Yeah, please see all the symbols here. What is NADP plus? NADP. No idea. No idea. But I can see you put some hydrogen ions onto NADP plus, and you end up with NADP. Quite interesting though. I just noticed, yeah, we've got sort of 2H pluses, NADP plus. Is that correct? I don't know. We shall see. Doesn't look very balanced to me. This is the opposite of electrochemistry. This is electrolysis. And if we're trying to make things like chlorine gas or sodium metal, this is the process by which we do it. We use electricity to actually reverse the electrochemistry. And in fact, this is actually how you go about recharging a battery. We have an electrical chemical process that sends the process forwards, which generates the electricity, and then if we have a reversible process, that is how we recharge the batteries. It also tells us why batteries run out eventually, because the process isn't fully reversible, and it also changes the material characteristics as you do that. So this is an electrochemical cell. This one is between zinc and silver, so it's silver plus, so it's silver nitrate and zinc chloride. We can see at the moment that the potassium would go towards the negative solution, and the chloride would go towards the thing that's generating the positive ions. So what's happening is it's drawing those through the salt bridge, which is why we really need a salt bridge and why it's really important that we use a saturated salt to make the salt bridge. Just checking I've actually turned my microphone on. I have, that's good. So, where does this all take us? This is called the electrochemical series, and we can see things here. So we've got fluorine here, which is an absolutely fantastic oxidizing agent. It has the potential of plus 2.87. And then we have something like zinc 2, which is a fantastic reducing agent. So if we think the species on the left-hand side are going to be more powerful oxidizing agents. So this is going to be the most powerful oxidizing agent that we have on this series. This is a slightly less powerful oxidizing agent. And this makes sense because if you think about it, fluorine is going to be a more powerful oxidizing agent than chlorine. And we see this when we're doing displacement reactions, and certainly with bromine and have we got iodine on here? Yeah, we can see actually we have the reactivity series here of the group 7 or group 17 elements. And we can see that actually this is why fluorine actually displaces chloride, why chlorine displaces bromide, why bromine displaces iodide. So what happens is, if I set up a electrode with chlorine and an electrode with iodine and iodide, because chlorine is the more positive, it will reverse the process for iodide. So we would find that actually the reaction would be fluorine plus 2 iodides becomes 2 fluorides plus iodine. So again, this shows you actually what all the displacement reactions you've been doing have been doing. So the more positive is written in the correct way, and then the more negative something is, and that can be smaller positive, but it can also be larger negative, will be reversed. We can also look at it another way. If we use, there we are, I'll go back and explain that in a short while. So if we have the silver plus ions becoming silver and the Cu2 plus ions becoming copper, which one is going to be the positive and which one's going to be the negative? Well, we can see that the higher positive number is here. We can see that the lower positive number is here. So this is the one that's going to be reversed. So what would the cell potential be? What would you get as a voltage? If I put these together, the cell potential is going to be the half cell potential for the positive terminal minus the half cell potential for the negative terminal, so the more negative value. So in this case, that would be 0.8 minus 0.34, and that would give us a cell potential of 0.46. So from that we could see which one was causing the other one to reverse, and we could also use them to measure the cell potentials if we know one of them. So the redox equation for this reaction, knowing that actually the Ag plus going to Ag is the most positive, that means that actually it's going to be the copper going to copper 2 is going to be on the left hand side of the equation, because that is the one that is reversed. So Cu goes to Cu2 plus 2 electrons, and we know that Ag plus an electron goes to Ag. We need to balance this one because the number of electrons are not matching. So what we do is we double the Ag plus and turn it into a 2 Ag plus 2 electrons becomes 2 Ag atoms. So what about these ones? Got zinc going to zinc 2 and copper 2 going to copper. Have a look and see which one is most positive, which one is most negative, and write the equations. We've got silver plus going to silver and copper 2 plus going to copper. Again, have a look and see what the answers are. We've got chlorine becoming chloride, and we've got Ag plus becoming Ag. So please look and see what the answers are. So, you guys worked out something called the Gibbs free energy, or we spoke about Gibbs free energy, and we know that Gibbs free energy, a reaction, can be spontaneous or feasible if Gibbs free energy is negative. And we can work out Gibbs free energy using this equation as well. And Gibbs free energy equals minus the number of electrons per mole of product times Faraday's constant, which is given here, times the cell potential. And if we think about it, if we want this to work, number of electrons is fixed, the Faraday's constant is fixed. In order for this to work, we must have a positive cell potential for the reaction to be feasible. So therefore, we must have a positive reaction, and that's why it reverses the less positive one. You do not need to remember this equation in the exam, so do not worry about remembering it. Guys, with these answers, just look up the PowerPoint. I'm just getting to the work. So please have a quick look, read pages 122 to 26. Make sure you answer the questions. Make sure you understand that the more positive is written forwards, and then the more negative is written backwards, and then you add the voltage of the more positive and take away the voltage from the less positive. I hope that works for you. What we'll work out next time is what happens when you change conditions to non-standard conditions. Thank you very much for your time.